Okay, let's dive right into this. Welcome to our explainer on kinematic graphs. Now, whether you are tackling Cambridge Additional Mathematics 606, Standard IGCSE Math 0580, O-Level Math 4024, or the advanced syllabus codes like 4037 and 4040, the principles we are about to cover are absolutely universal. Think of today's session like training for Olympic weightlifting. We call this the weightlifter strategy. Why? Because high-mark mathematics questions require maximum effort in short, explosive bursts. You need power, precision, and perfect form. To show you what I mean, let's look at a real Cambridge past paper challenge. Let's take two common approaches to past papers, looking at two hypothetical students. First, we have Alex. Now, Alex overloads his paper with raw mathematics facts. He throws every formula he knows onto the page, but there's zero analytical depth. He's trying to lift the weight with raw strength and absolutely no technique. Then we have Sam. Sam rushes, Sam sees the graph, panics, misses the specific command word requirements, and makes careless errors. You look at their papers side by side, and they are just covered in red pen marks from the examiner. Today, we are building your explosive mathematical power to transform those red marks into green check marks. We are going to turn those errors into absolute, undeniable precision. 15%. I really want that number to sink in for a second. 15%. That is the approximate weight this single topic, drawing and using kinematic graphs, carries in your total examination marks. It is a massive chunk of your final grade. Think about that. The examiners are looking for candidates who don't just blindly memorize formulas. Anyone can do that. They want candidates who execute high-level analytical thinking under immense pressure. You see, you need a structured, calculated approach to secure every single one of those marks. This 15% can literally be the difference between missing your target and securing that top-tier grade. It's the difference between a B and an A star. When you walk into that exam hall, you can't just hope for the best. You need a system, and that is exactly what we're going to build today.
So, here is our masterclass blueprint for today. First, we'll lock down core principles and theory. Second, we'll introduce the method mark strategy. And third, we'll expose the top 3 examiner traps.
Let's kick things off with Section 1, Core Principles and Foundation Theory.
Now, what's really interesting about this slide is that the most common examiner trap begins right at the definitions. Students constantly, and I mean constantly, confuse displacement with distance. Let's apply a framework here that top students use. It's called the PEEL framework. That stands for point, evidence, explanation, link. It's devastatingly effective in mathematics, especially when breaking down specific assessment objectives. To make your point accurately, you have to fundamentally know that distance is a scalar quantity. It is the total path traveled. Imagine walking around your block and ending up back at your front door. Your distance is the entire perimeter of the block. But displacement? Displacement is a vector. It's your exact positional change from the origin. In that walk around the block, your displacement is 0 because you ended up exactly where you started. If you apply the distance formula to a displacement graph without analyzing the directional shift, your foundational point in the PEEL framework is flawed and you lose the marks instantly. You must look at the axes first. Always ask yourself, are we tracking the total path or are we tracking the exact positional change? Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving deeper into the theory, we hit what I like to call the holy trinity of kinematic graphs: velocity, speed, and acceleration. You absolutely have to know the difference in your bones. Speed is your raw rate of movement. It's just how fast you are going, regardless of where you are headed. Velocity is your directional rate of change. It's speed, but with a specific direction attached to it. And acceleration is the rate at which that velocity is changing. Are you speeding up? Are you slowing down? Are you changing direction? For a velocity time graph, the gradient, the steepness of the line, represents the acceleration, and the area under the curve represents the displacement. The entire theoretical architecture of the Cambridge exam rests on understanding these causal relationships. If you see a flat horizontal line on a velocity time graph, you need to instantly know what that means. It means constant velocity, which translates to 0 acceleration. Knowing these exact translations gives you that explosive weightlifter power to answer quickly, confidently, and accurately without second-guessing yourself.
Here is something crucial straight from the Cambridge syllabus. It explicitly mandates that top-performing students must exhibit a conceptual understanding that seamlessly integrates with unfamiliar contexts. This is where the separation happens. This is where the A-star students leave everyone else behind. The examiner is not always going to give you a simple graph of a car driving down a straight road. They are going to give you a scenario you have never seen before.
Maybe it's a drone adjusting its altitude in a crosswind. Maybe it's a subatomic particle experiencing variable resistance in a fluid. It can seem incredibly intimidating at first glance, but here is the secret. You will look at that unfamiliar context and instantly connect it to the core concepts we just talked about. You will extract the underlying mathematical truth. You look at the drone problem and say, oh, wait a minute, this is just a velocity time graph where the area under the curve gives me the altitude of the drone. Connecting abstract math to a concrete, completely unfamiliar reality is the ultimate display of analytical depth.
That brings us to Section 2, the method mark strategy. This is all about the procedural framework. Let's imagine you are sitting in the exam, and you realize you've made a mistake, and you have just 60 seconds on the clock to completely rewrite a flawed answer. How do you do it? You use the standardized 5-step sequence. This is exactly what examiners are actively looking for when they grade your paper. Step 1, identify key elements. This means checking the axes, the units, and the scale. Step 2, apply relevant principles. This is where you decide, do I need to calculate an area here, or do I need to find a gradient? Step 3, execute analysis with clear working. Do not do it in your head. Lay out your numbers clearly on the page. Step 4, verify your results. Do they actually make sense in the context of the real-world problem? And Step 5, present in the appropriate format. Think of this as your mathematics success blueprint. When you see those red pen marks on our hypothetical students, Alex and Sam, it's because they skipped these steps. By following this 5-step sequence, we are transforming those before answers into brilliant, perfectly structured after answers. You are building an ironclad defense against losing careless marks. So the crucial point of this entire strategy is this: documenting your analytical framework literally equals points. The method mark strategy isn't just a nice suggestion, it is the fundamental rule of the game. Let me paint a picture for you. Let's say you need to calculate the area under a velocity time graph to find the distance. You do it all in your head, and you just write down 45 meters as your final answer. But oops, you misread the x-axis scale by a tiny fraction, so 45 is wrong. Guess what? You get 0 marks, nothing. But let's look at the alternative. If you write down the formula for the area of a triangle, you physically substitute the values you pulled from the graph onto the paper, and then you make a silly calculator error and write 42 meters, you will likely get the majority of the marks for that question. Why? Because you earned the method marks. You have proven to the examiner that you understand the physics and the math. The clear working is your insurance policy. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's keep building on this. Executing this specific sequence, deconstruct the question, extract the data, select your framework, execute the math, and present the answer does so much more than just get you the correct number at the end. It actually develops professional, high-level analytical skills. It trains you to use precise terminology. When you deconstruct a command word, let's say the question says evaluate, you instantly know you need to weigh evidence. You aren't just calculating, you are judging. Then you extract the raw data from the graph. You select your framework, like the Peel method we discussed earlier, to structure your logic. You execute the calculation flawlessly. And finally, you present it perfectly with the correct specific units. It is a foolproof step-by-step system that completely removes panic from the equation.
Moving into Section 3, the top 3 examiner traps. These are the classic mistakes students make when the pressure is on.
All right, it's time for an interactive workshop. We are going to run a 60-second challenge. I call this the data scan. Imagine a complex data chart is on your screen right now, and the timer is ticking down, 60 seconds. What are the traps you need to dodge while extracting the core trend? Trap number 1, using the wrong approach for the context. This is like frantically calculating a gradient when the question actually requires you to find the area under the curve. It's wasted energy. Trap number 2, unchecked formatting. You do all the math perfectly, but you forget to convert minutes to seconds or kilometers to meters. It is heartbreaking to lose marks on that. And trap number 3, the most dangerous one, failing the specific context. Let's say you do your data scan and you calculate the acceleration of a car, and you get -5. If you just write acceleration is -5 on your paper, you fall right into trap 3. You haven't described the motion in reality. To get the mark, you must translate the math back into the real world. You need to write, the car is decelerating at 5 meters per second squared. See the difference? Let's do another quick challenge. Challenge 2, find the flaw. I'm going to read you a flawed sample paragraph, and I want you to spot why it's losing marks. Listen closely. The gradient is 0, so acceleration is 0, which means velocity is constant.
Did you spot the flaw? It's a perfectly true theoretical fact, sure, but it is completely generic. It has no scenario application. Now, let's do challenge 3, speed writing. Imagine you have 30 seconds to write a perfect paragraph using the Peel framework for a graph about a parachutist falling from a plane. Here's what the top-tier, context-specific answer sounds like. Between 10 and 15 seconds, the gradient of the velocity time graph is 0. This indicates that the parachutist's acceleration is 0, and therefore the parachutist has reached a constant terminal velocity. Bam! Do you hear how much better that is? The generic answer gets a C. The context-specific answer, which names the parachutist and uses terms like terminal velocity, gets an A star. You must connect the abstract theory directly to the living scenario.
I want you to listen to this quote. This is directly from the principal examiner's reports at Cambridge. Quote, "Top-scoring candidates demonstrate evaluative thinking by questioning assumptions, considering different perspectives, and justifying decisions with evidence." This right here is the absolute pinnacle of our weightlifter strategy. When we talk about kinematic graphs, what does evaluative thinking actually mean? It means looking at a perfectly straight line on a graph and recognizing the underlying assumption. The graph assumes that acceleration is perfectly uniform. But you, as a top-tier candidate, know that in a real-world physics model, air resistance would likely make that acceleration variable. Identifying these built-in limitations and justifying your mathematical decisions with clear, written evidence is exactly what separates the elite candidates from the rest of the pack. You aren't just a calculator, you are a critical thinker.
So, let's bring it all together into the final system. This slide brilliantly illustrates the entire methodology in one easy-to-read cheat sheet. Think of these as the 3 rules that guarantee top marks. We have 3 cognitive domains. For the knowledge domain, your required action is to define terms precisely, decode those command words, and the trap to avoid, confusing speed and velocity, or distance and displacement. For the application domain, your required action is to use the Peel framework and show incredibly clear working. The trap to avoid, doing math in your head and losing those vital method marks. And finally, for the analysis domain, your required action is to manage your time so you can link everything back to the specific context. The trap, writing generic robotic answers. If you apply this time management matrix and master these 3 rules, you are locking in your success.
I want to leave you with this final provocative thought. Next time you sit down, open a past paper, and face a kinematic graph, ask yourself, are you just mindlessly calculating numbers on a page like our student Alex? Or are you truly evaluating the context of the motion, understanding the real-world physics, and strategically securing every single method mark available? The choice is entirely yours. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing right now. Our team actually responds to every single comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.